continue straight from previous video where we calculate the short-term deflection using the cracking moment of inertia, which is delta CR 14 millimeters that we calculated here at this particular point. And as you know that now the beam under this loading will also contribute into this cracking. If I draw the small pictures here, if I have a beam here, let's say you have a beam here, this beam, let's say you have a cracking develop in this flexures cracking here. Now in this case, what we assume this I crack was when you have this the concrete below this neutral axis, let's say this is neutral axis, is not taking any concrete stress, zero, but in reality there is this between the cracks, this concrete will contribute. So the stiffness is actually I crack is not correct. The actual stiffness is I effective. That's what the Australian standard say, which is basically I crack and I gross. So the I gross is when you have a cross section which is not cracked, is fully let's say this is a reinforcement and there is no cracking, then you have IG. I crack meaning that if you have a crack present, then you have ICR, but this ICR does not take into account the concrete contribution coming into the tension. Of course the concrete will contribute partially into the tension. So it's not here, but between the cracks it will carry some of this and it will increase the bending stiffness. So the when we done the test, I think that test will shows that it has some larger stiffness than the one that use crack. So we need to find these I effectives. Now the standards give us the equation straight away to find that I effective. That standards we're going to use that equations that I'm going to show you here in the close 8.5.3.1 on that next page. They have give you these I effective equations. Now in this I effectives we have all the values which is except this MS star, which is MS star is the maximum bending moment at the sections based on short-term serviceability load. Okay, so it's talking about maximum bending moment. So if you go back to this previous video where we know the maximum bending moments in this uniformly distributed load simply supported beam is WL square over 8, and please note this is given for short-term service load. So at short-term service load WS that we calculated in the last video. So 44, I can show it to you here. We calculated that 44 there you go, 44 kilonewton per meters. That's we calculated in the previous video where you can see that 44, that is a short-term service load. Now so it's very easy to calculate WL square over 8, 44 times, I keep it in the meters so I can get the answer in kilonewton meters. So 44 times 7 meters, 7 meters is the length of the beam over 8, 270 kilonewton meters. That's the moment, maximum bending moment. Now I effective, that equations again I copied from the standards on page number 129, that is shown here. Now in this equation I crack, that we calculated just in the last video. I crack was 3681 times 10 to the power 6. That's we calculated that we calculated this I crack. That's I substitute here 3681. 1 minus 1 I crack over I gross. I think we calculate the I gross as well, the moment of inertia which is on crack sections, that was 1 times 10 to the power 10 millimeter to the power 4. So that is I value. Cracking moments also we calculated. In this one you calculated the cracking moment was 20.4 kilonewton meters. That is substituted here. MS we just calculated MS 217. That will give us this effective moment of inertia 3694. Please always make sure that this effective moment is less than I cracking, but more than I cracking but less than I gross, meaning that this 3694 that would be greater than 3681, that looks correct, and that would be less than this 10,000 10 to the power 6. So that looks correct as well. there is a small check that we need to do it every time for the I effective. There was a I effective max. For that, if you calculate this tensile reinforcement ratio, which is P equal to AST on BD, and tensile reinforcement 1808, I think we calculated that 1808 tensile reinforcement 1808. That's I take it here, substitute here. B value is 350, D value is 645. It gives me 0.008. Now this standard saying that if your P value is greater than 0.005, your I effective max equal to I. Please note, for another case, when you have this condition less than 0.05, you have 0.6 I. So in our case, I effective equal to I, and we know this I we calculated on crack section 1 times 10 to the power 10. So condition is okay. 3694 is less than I max, so therefore this check is okay. Now deflection calculations, again we can go back to the structure analysis when we know this deflection is 5 WL4 over 384 EC, and this I is now I effective. We are taking this I effective, okay, not this I crack or I gross, because this is the actual graph, okay. This red one is the actual result. So we need to find the deflections, that is 5 times 44. I think that is the short-term loads coming on to the beam, which is 44 kilonewton per meters, times length of the beam is 7,000 millimeters, 7,000 millimeter to the power 4, 384 EC. I think that EC we also calculated in the last videos, where you have young modulus of the concrete taken from table 3.1.2, that EC. I effective, I think in this video we just calculated I effective, which is 3694 times 10 to the power 6. Give me 14 minutes, almost same as the I crack. It's not big difference here, okay. So that's keep in mind, but I think it's depending on your I effective and EC values, where it can be reduced the value. So that's the deflections at B3, so that is 14 millimeters here. Now it's in the questions is also asking us to find the long-term deflections, okay. So that is also asking to find the long-term deflection delta total. Now the equation for delta total is the short-term deflection plus these creep simplest factors times by the deflection due to the sustained loading for the long-term loading. Now delta S 40 millimeters we just calculated in this B3 40 millimeters, that was B33 that we just calculated. Creep and shrinkage factors, if you go back to these standards on the page number 130 on clause 8.5.3.2, it has these creep and shrinkage KCS factors given here, that I copied to take away 1.2 ASC over AST. Now the ASC stand for the compression reinforcement. Compression reinforcement we discussed it's 628, tensile reinforcement 1808 that we discussed in the previous video, that I substitute. The simplifications gives me 1.6 greater than 1.6. Now the standards also ask you to check whether this KCS is greater than 0.8. So we check it here. 1.6 is greater than 0.8, so therefore it's okay. Now the short-term deflections due to the sustained loading, that we need to calculate this W delta S as sustained. Now if you remember that we calculate the short-term loading, that's WS, we can't use this loading because it has these short-term factors. We need to recalculate this long-term loading coming on to the beam by dead load multiplied by these long-term factors. Now that long-term factors given in the questions, that is 0.4 and 30 dead load plus 0.4 times 20 give me 38 kilonewton per meter. Now so in that case delta sustain is 5 WL to the power 4 384 ECI effective. 5 38 we just calculated. Length of the beam is 7,000 millimeter to the power 4 384 EC 26700. I saw this one many times, so that is so this is delta sustain, which is 5 WL to the power 4, 5 times 38 times 7,000 to the power 4, 384. We saw you this one many times, and this I effective is 3694 times 10 to the power 6. That I effective we just calculated. I effective, I think I can show it to you here. that I effective we calculated 3694 times 10 to the power 6. So that's give us delta sustain 12 millimeters. So the total is a short term loading 14 millimeters that we just calculated for B3 14 millimeters plus 1.6 times 12 millimeters give us 33 millimeters. So that is the final answers for our total deflections. Thank you very much.